On this video, we'll work some more problems to prepare for the Chapter 8 test. So the first one, arcsine of x dx, is actually one of our integration by parts problems. So thinking of that Lipit, remember, is a suggestion for how to choose your u. And so a logarithm is a first choice, but we don't have a logarithm. The I stands for an inverse trig function, and that's what we have here. So we're going to follow that suggestion and say u is arcsine of x. That means dv must be our dx. It's just that 1. So the du is going to be the derivative of arcsine is the square root of 1 minus x squared, and v, the integral of 1, is going to be x. So as one of my students, or a bunch of my students, used to say, it's of dov. It's going to be uv minus the integral of v du is what we're going to actually work out. So the u times v is going to be x arcsine of x minus the integral of v du is going to be x times, so it's going to be x over the square root of 1 minus x squared dx. This we can do with a u-substitution. So we're going to say u is the inside of that radical. That makes du the negative 2x dx, and our dx will be du over a negative 2x. So this integral is going to be x over the square root of u, and then our dx is replaced by du over the negative 2x. We'll get rid of that pesky x, and we'll pull the negative 1/2 out. We'll write that in a more integral-friendly form, u to the negative 1/2. So we'll add 1 to the exponent, multiply by the reciprocal, and that will then become a negative square root of, what was our u again? In this case, it was the 1 minus x squared. And so let's put it all together. So I'm going to bring this back into play. So we have our x arc sine of x minus the square root of, wait, I think we left off, that was a minus a negative. So I think that'll become a plus the square root of 1 minus x squared plus c. There's going to be our integral. Now the next one, this is also an integration by parts, and this is one of the crazy ones that is not very satisfying, but we're going to go with the Lipit. So let's see, no logarithm, no inverse trig function, no polynomial, so exponential is our next choice. So we're going to say e to the 1/2 x is our u. That makes dv the sine x dx. So the du is going to be e to the u times the derivative of the exponent, and the v, the integral of sine x, is going to be a negative cosine of x. So far we have our u v minus the integral of v du. Looks like u times v is going to be a negative e to the 1/2 x cosine x minus our integral of v du. So our v is a negative cosine x, so I'm going to bring that negative out. So we're going to have our v, and then our du is that 1/2 e to the 1/2 x dx. So that doesn't look any better than our original, but I'm going to change color so we can keep it straight. So now we're going to do it again. So again, staying consistent, I'm going to say u is that 1/2 e to the 1/2 x, and the dv is going to now be the cosine of x dx. So du is now going to be a 1/4 e to the 1/2 x, and our v is going to be a sine x. So let's see, I'm going to bring it down over here. So here's our equal sign. we already have that e to the 1/2 x cosine of x, and now we're going to go plus, and u times v is going to be a 1/2 e to the 1/2 x sine of x minus the integral of v du, which is going to be, I'm going to bring the 1/4 out on this one. Here's our e to the 1/2 x sine x dx. And remember, our original was that integral of e to the 1/2 x sine of x dx. So at first we may throw up our hands and say, oh no, look, right back exactly where we started, but this is actually good. Now we're going to think of it not like a calculus problem, but like an algebra problem. So we are going to add a 1/4 integral of e to the 1/2 x sine of x dx to both sides. So when we do, we see that we have exactly the same integrals. So one of these plus 1/4 of those makes 5/4 integral of e to the 1/2 x sine of x dx is equal to e to the 1/2 x cosine x plus 1/2 e to the 1/2 x sine of x. So we're now going to multiply by the reciprocal, and so we're going to say our answer to this integral e to the 1/2 x sine x dx is going to be 4/5, and I'm just going to throw it all in a big bracket here, e to the 1/2 x cosine x plus 1/2 e to the 1/2 x sine x, and don't forget the plus c after all that. That's crazily enough is our answer. And you can distribute that if you want. Okay, let's slide up. This is a challenging integral, and there are many hurdles along the way. The first is what to call u, and that's going to be 1 plus the square root of 3x. Now du is the next hurdle because we have a chain rule derivative. Remember, we're looking at that square root of 3x as 3x quantity to the 1/2. So that's 1/2 times 3x to the negative 1/2 times the derivative of the inside function 3. So I'm going to write that. The 3 is going to stay up in the numerator. The 2 from the 1/2 will join our negative exponent in the denominator. So that means that dx is going to be 2 square root of 3x all over 3 times du. So our integral now looks like 2 over, that whole denominator is u, the dx is being replaced by all of this, 2 square root of 3x over 3. Now we can't go on because we still have x's in there. Well, there's a lot of stuff in there. We're going to pull the constants. The 2 times 2 is 4 over 3. We're going to pull all of that outside the integral. And now we're going to try to figure out what to do with this square root of 3x. So we come back to our u-substitution and see that we can say that square root of 3x is actually u minus 1. So that's going to make, I'm going to come down here a little bit. So that's going to make our integral now 4/3, and that's going to become a u minus 1 over u du. We're making progress, but still a few challenges to try to figure out. So I'm going to split up that into u over u minus 1 over u, and so that is going to be 1 minus 1 over u du. Now be careful. The integral of 1 with respect to u is going to be u, not x. We're going to get a 4/3 times the natural log of u, and then we're going to go back to our x's. So our u was the 1 plus square root of 3x minus the 4/3 natural log, and you can go with or without absolute values, because 1 plus square root of 3x can never be negative, plus c. That is one tough integral. All right, looking at the next one, I think the best way to do this is to split it apart and then simplify each of those fractions that have their own denominator. So the first one, we subtract exponents. 2x minus 1x is x, so this becomes the integral just of e to the x. The second one's even better. The e to the x's cancel. Now, we're way ahead of the game if we think of 1 over e to the x as e to the negative x. That's a much easier integral to do than to try to figure out what to do with 1 over e to the x. So the integral of e to the x is e to the x. The integral of 3 is 3x. The integral of e to the negative x, we can, even in your head, say that the u is going to be the exponent, and so that's going to become e to the u, and we'll get an extra negative sign. So that's going to, the extra negative sign is going to make that a plus 2 e to the negative x plus c. So there is that integral. The key, I think, is dividing up the fraction into separate pieces. Okay. The next one is a tough one. So we have a choice here. There's kind of two ways of doing it. One way is to multiply top and bottom by e to the negative x. That's going to make this into e to the negative x. When we distribute that e to the negative x in the denominator, e to the x times e to the negative x is e to the 0, which is 1, and 1 times e to the negative x is e to the negative x. That makes our u 1 plus e to the negative x, and our du becomes negative e to the negative x dx, and so the dx is going to be 1 over our negative e to the negative x du. So our integral, there's the e to the x from the negative x from the original. We have the denominator is our u, and we're going to get du over, and here's a negative e to the negative x. That will cancel those e to the negative x's. We'll get an extra negative sign, so it'll be a negative natural log of u, which is going to be a negative natural log of 1 plus e to the negative x. And you don't have to have the absolute values there, because that'll never be negative. Now, an alternative way to do that is to say, well, let's add an e to the x and then subtract it off to make our denominator now, or our integral, look like that. So I'm going to change colors here so we can distinguish. So then we're going to write that as the 1 plus e to the x over 1 plus e to the x, and then we're going to get a minus, and here's an integral of e to the x over e to the x plus 1. So on the first one, that's just the integral of 1, which is going to be just x. And on the next one, we can say u is that denominator, and du is its derivative, and that makes dx du over e to the x. That makes our integral u in the denominator and du over e to the x, and we get to the integral of 1 over u du. So we get x minus the natural log of u, which, remember, was this e to the x plus 1, and you do not have to have the absolute values, and they look very different, but crazily enough, they will both have a derivative that will get you back to the integrand, 1 over e to the x plus 1. So on the next one, we're going to have to do an integration by parts again. So our u is going to be x, and our dv is going to be e to the 3x. The du is very nice, it's just 1. The v, the integral of that, is going to be e to the 3x, but we need a 1/3 to cancel, so that when we differentiate it, we get back to the dv. So now our integral is going to be u v minus the integral of v du. So u times v is going to be 1/3 x e to the 3x minus the integral of v du, and I'm going to pull the 1/3 out, and we get another e to the 3x dx. You can do a u substitution if you like, or if you can do it in your head, that's okay too. And we're going to, at the end of the day, get this e to the u, and we're going to get an extra over 3. So we're going to get 1/3 x e to the 3x. That's going to be a minus 1/9. The integral of e to the u is e to the u, so we get another e to the 3x, and then our constant of integration. So there's what we're trying to get. Okay, let's look at the region bounded by x equals 3y minus y squared and the y-axis. Set up the integrals, but we don't have to solve them. First for the area. Well, let's get a little idea of what this looks like. So if you imagine factoring the y out, you can see that x will be 0 when y is 0, and also when y is 3. And it's going to be a parabola that opens to the left. So there is our function. We are going to imagine first so we're looking for the region bounded by this. So our rectangles are going to probably need to be horizontal, and we're going to think of our delta area as being base times height, and the base is going to be the right curve minus the left. So it's going to be the x-coordinate of that point. The height of our rectangle is going to be a delta y. So that means we need everything in terms of y, but that's okay. That's what we had. So our delta area is going to be the x, which is 3y minus y squared times a delta y. So our integral for the area is going to go from the 0 to 3 are those y limits, and it's going to be the 3y minus y squared dy. So there is our integral, and we don't have to actually evaluate it. Now we're going to imagine revolving that about the y-axis. So we're going to use our same rectangle. As we spin that rectangle around the y-axis, we're going to get a disk. And a disk has a delta volume of pi r squared h. The radius of our disk is going to be that x-coordinate there, which again is going to be the 3y minus y squared, and that radius is going to get squared. I forgot the pi. And our height of our disk is going to be that little delta y. That makes our volume, pi, again we're integrating from 0 to 3, of 3y minus y squared squared dy. Okay, then we'll try about the x-axis. So to spin that around the x-axis, we're taking that same little rectangle, and as we spin it around there, we can see that our rectangle is parallel to our axis of revolution. So our delta volume is going to be a shell, which is 2 pi r h delta something. In our case, it's going to be a delta y. So let me get the eraser up there. So it's going to be for us a delta y. So we have 2 pi. Now the radius is that distance from the axis of revolution out to that rectangle, which is going to be the top curve minus the bottom curve, or you can say this distance is going to be the y-coordinate of that point. So our radius is going to be y. The height of our shell. I'm going to redraw it maybe over here, so I'm going to turn it around. So the height of our shell is this distance here, which is right curve minus left, which is our 3y minus y squared, and then our thickness is going to be a delta y. So our volume is going to be, we'll pull out the 2 pi, still going from the y limit 0 to 3, and we can either distribute that or not. Either way is equally acceptable. And that is going to give us the volume when we revolve around the x-axis. Okay, now about the line x equals negative 5. So x equals negative 5 would be that vertical line over here. So as we spin that around, and you keep your eye on that little rectangle, when it spins around, what we're going to get is this thing that looks like what we're going to call a washer. So our washer has a delta volume that's going to be pi outside radius squared minus the inside radius squared times our thickness, which is going to still be a delta y. So our outside radius goes from the axis of revolution out to the outer edge of that solid. That's a horizontal distance, so we're going to go right minus left. So this point right here is going to be the x-coordinate of that point on the curve minus that vertical line, which was at a negative 5. So that radius is going to be in x minus the negative 5. But since we have a delta y, we need that x to be in terms of y, which means it's going to be our curve. So that's going to be the 3y minus y squared minus the negative 5 will be a plus 5. That's our outside radius. So far we have pi times, and we're going to get that 3y minus y squared plus 5 squared minus the inside radius, which is going to be that distance from the axis of revolution to the edge of the hole. But the right there is always the y-axis, which is x equals 0. 0 minus negative 5 is just 5, so that's going to be 5 squared. So our volume is going to be pi. We'll pull that out. Integral again from 0 to 3. We're going to get 3y minus y squared plus 5 squared minus 25 dy. Okie doke. Let's try about the line y equals negative 2. So the line y equals negative 2 is going to be down here. So there's y equals negative 2. So now what we're going to get again is our rectangle is parallel, parashell. So we're going to get a shell. So our delta volume is going to be 2 pi r h and then a delta y. Now the radius is typically the hard part. It's going to be that distance from the axis of revolution out to that little rectangle. So we're going to go top minus bottom. So the top right there is going to be just the y coordinate of that point minus the negative 2. So our radius is going to be y minus negative 2. That is, it's going to be y plus 2. So that's going to, whoops, I got it in the wrong place there. Let me move that. So our r, if I can get it to scroll, so our r is going to be the y minus negative 2, which is y plus 2. So there's the radius. The height is again going to be that in our shell, which is going to look very thin. So it's a very thin cylinder there. So the height of our shell is going to just be our function. It's going to be that distance right in there. And so that's going to be our, I kind of ran out of room there. So our height is going to be the 3y minus y squared. So our delta volume is going to be 2 pi times the radius times our height, which is 3y minus y squared, delta y, making the volume our integral, 2 pi times the integral from 0 to 3 of the y plus 2 times the 3y minus y squared dy. Okie doke. Now about the line y equals 4. So scrolling back up here, y equals 4 is going to be somewhere up there. So again, we are going to be parallel. So we're looking at a shell method again. So our delta volume is going to be 2 pi RH times a delta y. Again, the challenging part is that radius. And that radius, did I go past it? There we go. The radius is going to be that distance from the axis of revolution to our rectangle. We're going to go top minus bottom. So that's going to be the 4 minus that y value. So we're going to go 4 minus y is going to be our, trying to get my pen back up. So it's going to be a 4 minus y for the radius. Our height is again going to be the 3y minus y squared and a delta y. So our volume is going to be 2 pi, integral from 0 to 3, 4 minus y times 3y minus y squared dy. Okie doke. Let's go cross sections perpendicular to the x-axis that are semicircles. And just kind of redraw over here. Remember, we got this sideways parabola, and we're taking our rectangles perpendicular to the y-axis. So we're saying that we've got coming out from the iPad here a semicircle. This is what we're looking at, our cross-sectional piece. And so our delta volume is going to be the area of that cross-sectional piece times delta y. So it's a semicircle, which means it's going to be 1/2 pi r squared times our delta y. This distance, the diameter, is our function, 3y minus y squared. So the radius is going to be 3y minus y squared over 2. So our delta volume is going to be pi, right, do that at the same level, so there's pi times our radius, which is 3y, it's a half circle, pi over 2, 3y minus y squared over 2 squared delta y. So that denominator gets squared, and we can pull that out as a pi over 8, integral from 0 to 3 of 3y minus y squared squared dy. There is our semicircle. So our quarter circle, if we imagine that we're getting something like that with a little bit of thickness, delta y. So again, this is coming out of our iPad as a quarter circle there. That's what we're looking at. And we know that our delta volume is going to be the area of our cross-sectional piece, not in terms of y though. I think I said that before. That should really be in terms of y. Let me change that and fix that on the other. So that should really be a of y. So a quarter circle is going to be 1/4 pi r squared times our delta y. So that's going to be a pi over 4 times, and our radius in this case is just our function, and then we have a delta y. So our volume is going to be pi over 4 is the constant that comes out, and we get that 3y minus y squared dy. Okie doke. The next one, equilateral triangles are the hardest. So we are going to imagine that, here's our parabola, there's our rectangle, and we're getting these equilateral triangles. So you have a little bit of thickness to them. So our delta volume is again going to be the area with respect to y, delta y. That's going to be 1/2 base times height times delta y. And our base is going to be just our function. So 3y minus y squared is that distance across there. When we drop the perpendicular down to get the height, we create a 30, 60, 90 triangle. In a 30, 60, 90, we know the side lengths go x, 2x, and our height is going to be x squared root of 3. So that makes our height this distance, which is that's going to be our x. So it's going to be that 3y minus y squared over 2 times the square root of 3, or we can say there's a 1/2. Our base is the 3y minus y squared. Our height is going to be a square root of 3 over 2 times another 3y minus y squared, and then our delta y. So that means our volume is going to be the constant that we pull out, turns out to be a square root of 3 over 4 integral from 0 to 3 of the 3y minus y squared dy. Okay, isosceles right triangle with the leg on the region R. So here's that little rectangle, and what we mean is that the leg is on there. So we're going to look at something that's going to be this right triangle, and it's the leg that is going to be on our iPad or on that region. So we know that our delta volume is going to be the area times delta y, and the area of a triangle is 1/2 base times height. So our base is going to be that 3y minus y squared. Now the height, since it's isosceles, those two legs are the same, and so that means that the height is the same as the base, it's the function, which means that our volume is going to just have a 1/2 integral from 0 to 3 of 3y minus y squared dy. Okay, and now we're going to do our isosceles right triangle with the hypotenuse. So here's our rectangle laying on there. Now we're going to imagine that that's the hypotenuse. So it's going to look something like that, where there's the right angle. So again, our delta volume is going to be 1/2 base times height, the area, times a delta y. So the base is going to be just our function. That's the 3y minus y squared. Now when we draw in that height, so when we drop in that perpendicular there, since our original had a 45-degree angle there, we drop in that perpendicular, we just get a small version of a 45, 45, 90. So that means this height is the same as that leg, and that leg is half of our original base. So that's going to be another 1/2 3y minus y squared, and then our delta y. So that makes our volume 1/4 times the integral from 0 to 3 of 3y minus y squared dy. Okay, very good. I think we got a couple more challenging integrals. So let's see, on this one, we're going to try letting the u be that exponent, the cube root of x, which we're going to think of as x to the 1/3. That makes du 1/3 x to the negative 2/3 dx, which it might be a little easier to think of that as 1/3 times the cube root of x squared dx, making the dx 3 times the cube root of x squared du. So our integral now comes together. We have e to the u, and we look at that, what looked like a troublesome denominator, but we are going to exactly match that with our dx, and so those will cancel except for the extra 3, and so we're getting 3 times the integral of e du, which is going to be 3e to the u, which is 3e to the, we said that was the cube root of x plus c. And there's our answer. Okay, let's try the next one. Let's do our e to the 1 over x squared x cubed. Again, we're going to try letting our u be the exponent. Oops, that's x squared. Let me fix that. So that's 1 over x squared, which we're going to think of as x to the negative 2. So du is 2x to the negative 3, which means dx is going to be, we're going to get a negative 1/2, and then moving that x to the negative 3 to the other side is going to be 1 over x to the third du. So our integral becomes e to the u. We've got that x to the third, and our dx is going to be a negative 1/2 x to the third du. And we exactly match that x to the third. We pull the negative 1/2 out, and we get our favorite integral, which is e to the u, which our u is that 1 over x squared, and plus our constant of integration. So the next one, again, we're going to say, let's try u is the exponent, square root of x, which we're going to think of as x to the 1/2. That makes du 1/2 x to the negative 1/2 dx, which is 1 over 2 square root of x. So solving for the dx is 2 square root of x times du. So our integral becomes 5 to the u. I'm going to leave that as a square root of x for a moment, but that's soon going to get canceled by our dx. And so we will pull that extra 2 out, and these are not our favorite integrals, but it's going to be 2 times 5 to the u, which we said was square root of x, over the natural log of 5, and then plus c. Yuck. Now you cannot say that 2 times the 5 to that power is 10, so refrain from doing that because of the order of operations. Now this one, we'll start by exploring a little bit and say maybe u can be the whole inside of the radical. That would make du be 2 minus 2x dx. And if we say, if we factored out maybe a negative 2, that would be then a negative 1 plus x du. And so the dx would be our du over a negative 2, and I'm going to write that as an x minus 1. We look at our integral and say, oh man, if only we had a minus 1 there, it would be perfect. So we're going to put it in. So we're going to split it up now, and we're going to go x minus 1, square root of u, and the dx is our du over a negative 2 times x minus 1, and we're well on our way. But we're still going to have this other integral of the plus 1 over that square root of 2x minus x squared. We'll come back to that. We can cancel our x minus 1s, and this integral is coming along swimmingly. We have u to the negative 1/2 du, so that's going to be u to the 1/2 times 2 times that extra negative 1/2, so that's going to be a negative square root of, and our u was that 2x minus x squared. Now we got to do the other part. Now this, we don't have an x up here, so we can't use that same u-substitution that we did earlier. So we're thinking this is going to have to become an inverse trig function. And because we have a square root, it's either an arcsine or an arcsecant. Because we have a minus x squared, we're going to try to move forward as if this is going to be an arcsine. So when you factor that negative out, the 2x becomes a negative 2x. we take half the middle term, square it, and add that in. But that's really a negative 1, so we turn back around and add in 1. So our integral now looks like 1 over the square root of 1 minus, and our u is going to be x minus 1 squared. So that is the 1 minus u squared that we were after. Our u is going to be pretty benign because the du is just dx. And so we get the integral of 1 over the square root of 1 minus u squared, and we just trade the dx in for a du, and we're going to get our arcsine of u, which we said was an x minus 1. So our final answer is this negative square root of 2x minus x squared plus the arcsine of x minus 1 plus our constant of integration. I think this might be mercifully coming to an end. Yep. Okay, very good.